Sorry. You're
Yeah,
not
now I'm recording. Now I'm
okay,
recording. Sorry. Yeah.
Oh,
Thank you.
okay. So Zara, we don't know the order. In fact, we are choosing the order ourselves. Good. So in the second example also, we are given n boxes, each of which is a random variable, really. So I think of these random variables as boxes. If you open the box, you reveal the value of the random variable. Initially, you only know the distribution. You want to find the maximum of these, but you're only allowed to probe b of these boxes. Say b is 2 in this case. So you're allowed to open 2 of these boxes, and then you choose one of the choices you made. So what can you do? You choose the first box. It was supposed to be uniform in the interval 0, 1. It turned out to be 0.6. And now you say, okay, well, what should I do? What should I try? Well, clearly I shouldn't try this guy because he's going to be 0.2 and I already have 0.6. I want to pick the maximum. I want to pick a large value. Okay. So clearly this is a crappy box to pick. I could try this, or I could go for broke. I could say, I'm feeling lucky today. Maybe I'm going to succeed. So maybe I try this last box. And it turns out, I was unlucky. It's okay. So I got 0.6. So for different values, I might try different things. Like for instance, if the first box gave me 0.001, I might say, look, I'm risk averse. I'll pick this box instead. I'm guaranteed 0.2. Something like this. Good. So the whole thing is one operation is allowed. You open a box. You look at a random variable. Its value is revealed. And you go on. And you stop when you've looked at b of these things. And this constraint is just, I'm choosing one possible constraint that I could have chosen. You could imagine various other constraints. This is a very general model in some sense. I'm given this region, and I know that the probability of treasure in all these locations. I want to maximize the probability of treasure. I only have until noon for my treasure hunt. What should I do? Replace treasure with oil fields and replace, whatever, until time t with, the amount of money that I have. You can come up with, these kind of problems arise all the time. And you really, so how do you solve these things? Okay, good. The problem, we good? Good, okay. So there are two things. One is, these are simple ideas and I'll go over them, somewhat fast, but okay. So the main idea is that the best algorithm could be an adaptive strategy. It could be something like, I look at the first, I figure out which random variable to look at first, which box to open first. Conditioned on the value that I saw, I might decide to do various different things. I might decide to open some other box. Okay, so for instance, if I had two random variables, both of which were, unbiased coin tosses, you get one with probability half, and then x3 is you get $10, but with small probability. Right? So, and suppose you were allowed to pick two boxes. Now, here is a reasonable thing you could try. You might say, I'm going to try x1. And if it comes up 1, I might actually decide, I'm going to try, be more risky. But on the other hand, if it came up 0, then I might decide, no, I want to be risk averse. Right? So that's a very reasonable strategy. And in fact, if you are trying to maximize your reward, this is indeed the strategy you would pick. Maximize your expected reward. It's very simple, there's only so many objects out here. You're allowed to pick two of these guys. You can run over all possible options. This is clearly the only reasonable option to do. Okay, good. Okay, so this is a gold standard, an adaptive strategy. It's a decision tree. What do I do first? Condition on what I saw. What do I do next? And so on and so forth. Okay. One thing to note is that these decision trees could be exponentially sized or even infinitely sized, right? I mean, it depends on whether the values are continuous or whether they're discrete. Let's even say values are continuous, just for the time being. Oh, sorry, values are discrete, just for the time being. It makes our life much easier. Okay. So these things, if you have so many, if you have B choices to make, they could be like n to the B. There are n choices for the first one, then conditioned on whatever you saw, there are at least n choices for the second one, n minus 1 choices for the second one, and so on and so forth. Right? So these things, there are many of these guys. They're exponentially sized. So the point is, finding even writing these things down might take too much time. Okay, good. But this is the gold standard. This is what we want to compare against. This is opt. Okay. By the way, you can solve for most of these problems using dynamic programming. Assuming, let's assume that things were discrete. So you could say, if I were allowed to open one box, what should I do? And if I were allowed to open 2 boxes, then having looked at the first box, now I look at all possible choices for the second box. So you can actually write down a dynamic program, and maybe I should have given this as an exercise for the discrete valued B box problem. Good. So if the boxes are independent, why is it not the expected value? See, the thing is, the boxes are independent, but you're not allowed to open the box again and again. So, conditioned on what you have seen so far, that option is not there anymore. Okay. So you can say, look, given that I cannot open boxes 1, 3, 7, and 9 anymore, what is the best option? That's what you need to solve right now. Good. So what you would design is you would design a tree saying, like, look, so let's actually go back to this example. So in this case, the expected value, absolutely. Thank you. Yep. So here, when you've come here, condition on you've opened x1, and actually, Pedro, you are right. I should have said you're opening you are solving the problem saying I've opened 1, 3, 7, and 9, and the maximum I've seen is 17. So that's one more piece of information that I have. And so this is why I need to know the history. Does this help? Does this clarify matters? Okay. So let's go on, and do ask if things don't get clear. So one thing you could do is you could say, look, writing down this adaptive policy takes too much space, takes too much time. Instead, I'm going to write down a non-adaptive policy. And in fact, it's going to be exactly a sequence and not a tree. I'm going to open up x3, and then I'm going to open up x4, and I'm not going to look at what the values are so far, let's say. So I'm not going to be adaptive. So in some sense, I have a massive list. I look at the first one, then I look at the second one, then I look at B of these guys, I stop. Okay. Good. So this is non-adaptive policy. It's very nice. It's compact, but of course, it might have less value. Okay. And the gap between an adaptive and a non-adaptive policy is exactly what we'll call the adaptivity gap. That's it. Just a piece of jargon. Good. So let's just do a little example. This is the same example from before, where we had two unbiased coins and one, high reward, high risk coin, and we got 79%, 0.79 as our reward. On the other hand, the best, if you can run over all possible choices of two boxes to open, and you'll see that the best thing to do is open X1, then open X2, and you're going to get 75% as a maximum. You fail only when both of these come up to be tails, which is 25% of the time. Okay, so the gap in this case is whatever. 79 over 75, pretty much. Okay. So for the B box problem, you know that the adaptivity gap is at least this much. And what you would like to get is you would like to also get upper bounds on the adaptivity gap. Okay. Good. And in general, this question of this is exactly the sort of problem that suppose I wanted to give a non-adaptive strategy, which is comparable to the best adaptive strategy. How do I even argue about the adaptive strategy? Good. So Thomas asks, this adaptive strategy is better than taking all B combinations of boxes and then choosing the one with the highest expectation. So in fact, taking all B combinations of boxes and choosing the one with the highest expectation will give me the best non-adaptive policy. And what I want is I want to say, well, how good is this best non-adaptive policy to the best adaptive policy? There's the second question of how do you find the best non-adaptive policy fast? We can come to that as well. Good. And is the reward the sum or the max? In this case, it's the max. Thank you. Sweet. The rewards is the same distributions, then would the optimal policy with different parameters. Okay, so the question is, if the random variables, should I just order by the expected value and go with that? The answer, okay, I'll have to think about that. The answer, my guess is no, but I'd have to think about an example for this. So let me defer that question. Gaurav, ask me again in a little while, and hopefully I'll have the answer to that. Okay, but almost certainly the answer is no. Okay, good. Okay, and as always, we are looking at approximation algorithms. Okay, so what's the ideal result? The ideal result is a polytime computable non-adaptive policy. I want a policy which is non-adaptive, which is comparable to the best adaptive policy. Okay, so I want to give an algorithm which is computable fast, but also good compared to the adaptive policy. So I want to bound the adaptivity gap. Okay, so let enough with the preamble. Let me dive right in. Let me give you an algorithm that's going to work for good adaptivity for the B box problem. Okay. So I'm going to use LP relaxations. I'm going to use linear programs. See, the thing is, I need to compare to the best decision tree. And this is a pain, right? I mean, these things are exponentially sized. I have difficulty sort of visualizing exactly what they are. What I can do is I can write down certain, necessary conditions or certain marginals for what this thing is doing and then compare to that. And linear programs are great for doing this. It'll turn out. So let me show you how. So how do I generally use linear programs? We saw this in the first couple of lectures. You take a discrete problem, you write it as an ILP, you relax it, and then you round it. Right? We saw the relax and round, whatever. So here's what I'm going to do. I'm going to take my stochastic problem. I'm going to write an LP whose value is comparable. So you should think of this as being a surrogate. It's going to be a relaxation. Sometimes we think of this as being a projection, and you'll see why, of the problem. I'm going to write an LP whose value is going to be pretty good, just as before. And then I'm going to round it, and I'm going to get an integer solution. And I'm going to have to interpret this as a stochastic policy. Okay? This might not make that much sense right now. You'll come back to this in a moment. Let's do the thing for best, the best box problem. Remember, n random variables, independent, known distributions. And let's say that these outcomes are discrete in 0 through n. Okay. And the examples on the right-hand side are not discrete, but whatever. Or maybe I've made them discrete finally. Yeah, okay, good. They're discrete. That's okay. You can open B boxes, and then you choose one of those boxes, gets its value. Stop. Maximize the expected value. Okay, good. Good. So there is some optimal decision tree. This is let's say this is the optimal decision tree. I'm going to write down some valid constraints on these things. Okay, so let's look at the following. This is one path down the decision tree. This path has, says open the box 1, then open the box 3, get $10. So the choices are, I open something, I open B things, and then I choose one of them at a certain value. Okay. This last choice is almost forced because I'm taking the max. But let me think of this as making a choice. Okay. Here's a different one. I'm going to, if I saw these options on this path, the max is x1. So I'm going to choose x1 at value 1. So just bear with me. It's just this sort of, I want to think of this as making a sequence of decisions about opening boxes and then making a choice. Does this make, this kind of makes sense? This is a very simple idea, right? Okay, good. So here are some constraints I can write down on every decision path. Okay. Suppose I look at this decision path, this blue one that I've drawn on the left. Our value is, well, it's, this is an indicator. This is 1 if this action were actually taken. If I chose some random variable, some of these boxes, one of these boxes at value v, then I'll get a total of v. I can choose I at value v only if I open I and I see value v. The number of choices I make is at most 1. The number of boxes I open is at most b. And this is true on this path, on this path, on every path down this decision tree. This is what it means to be feasible. I mean, these two are meant to be feasible. This is just saying, well, if you open it, if you choose it at that value, you must have opened it, and that value must have come up.
Sorry, so the first sum is over all decision path, right? Or I kind of
so in this case, I'm actually saying our value on this decision path, let's say. R value on this decision path is just saying on this decision path, did I choose I at value V? And then, okay. So there's one little thing out here that I want you to see. This is because of independence. The fact that I can, the value, so normally I should say, well, actually in this case, I don't really what I should do is I should say it's the indicator of open I. So maybe I should write this as indicator of open I and xi equals v. Let me write it that way. If I choose I at v, it better be the case that I opened I and I xi took on value v. Okay. And if I do this and I take the expectation over all paths, over all decision paths, each of these indicators will turn into probabilities. So this will say, so like this first line will become our expected value is equal to sum, exactly as you said, over I and V of the probability that the strategy chooses I at V. These things will say the total probability of choosing I at V is at most 1. So in fact, if xi is the probability that this massive decision tree open box I at any point, what is this decision tree? You do the first action, you come to one of its children randomly. You do the next action, you come to one of its children randomly. You go down this tree. So xi is the probability that this decision tree opens box I. So for instance, if we went back to this strategy, let me just clear the thing. So in this strategy, the probability that I opened up box 1 is 1. I always open up box 1. The probability that I opened up box 3, and I'm sorry about using little x's and big x's for two different things. It's a common mistake. Okay. Little x3 is the probability that this strategy opens up box 3. What's the probability? Well, it only happens if the root came up left, which happens with probability half. And x2, little x2 is also half. Okay. Similarly, you can write down things like what's the probability that box I, I chose box I at value v. So here I will say the probability that I chose box 3 at value 10 is, well, I must have come up with probability half. And then this happened with probability 1 over 100 or something like this. So this is 1 over half times 1 over 100. Okay. And, I'll choose x1 at value 1, either if I came down this road or I came down this road, let's say. Actually, no, I came down only the left road. So the eventual point is that if xi is the probability that the strategy opens box I and yiv is the probability that the strategy chooses box I at value v, then you get these constraints that the sum of the xi's is at most b, that's coming from this.
So Anupam, can I ask a question?
Please.
Just to see whether I'm following.
Absolutely.
Precisely. So when you compute YIV, in some sense, you are summing up over all paths that have a value V and uses the box I.
Absolutely. So this is saying that in this decision tree, or the leaves, at the leaves, I'm making some decisions. I'm choosing some box at some value. And let's look at all possible leaves where I chose box I at value V.
But the choice is only at the leaf. Is when I chose box I.
Let's say this is what's happening in the optimal decision tree. For the optimal decision tree, there is no reason for it to choose early.
Yeah, but you're relaxing, so that's why you need to model as a decision, right? Or
Absolutely.
Is this a problem? Yeah, because you want to relax it.
In some sense, these are things that my optimal decision tree is doing. It is opening a bunch of boxes, and it's making choices of boxes at values later on. And what I would like to do is I would just like to not worry about the path you took to these choices, but just what is the probability of these choices. So you might choose box 1 at value 1 in 23 different ways down this tree. Let me not worry about that because there's just too many of them. I'll just say what's the probability with which box I got chosen at this value. Somebody asked another question. Good. So Pedro is asking, how would you reconstruct the optimal tree? And the point is, I don't want to reconstruct the optimal tree because it's too large. It's exponential size. I can't write it down. But what I can do is I can construct a near optimal tree just from these marginals. And you'll see.
Sorry, I asked whether, so the reason you kind of replace this decision, taking the maximum, like instead of doing this, like making a decision, is because you want to relax you want or you need to relax this variable, or because originally we just kind of take the maximum instead of like saying that actually we make a decision, right?
Good. So what I want to do is I want to kind of relate. So look at this constraint. It is because I'm trying to relax it, but maybe let me say one more word about this. I want to make sure that I choose value V. Actually, you know what? Yep. The simpler answer is it's because it'll help me come up with the algorithm. And you'll see. Just hang on for a slide. Okay. So what I want you to just take away from this is if these were two objects that you were looking at, two quantities, not two, but each of these is a collection, But if you're looking at these quantities, they satisfy these constraints. Our value is this. And for the second line, I'm using independence. I'm using the fact, so, I had that mistake on the previous slide. This should really be, it's the indicator of open I and xi equals v. And if I take expectations, this becomes the probability that I open I and xi equals v. And the probability of a random variable taking on a value does not depend on whether I opened it or not, because they are independent. If they were dependent, if there were two variables which were exactly the same, I might open it up knowing that it's going to be high. But because they are independent, this is just probability that I open I times the probability that xi equals v. And that this is just saying the probability that I open I, and this is just the probability that xi equals v. This is just shorthand. Okay. So I want you to think of the following thing. The total number of choices I made is at most one. At whatever value, I don't care. the total number of boxes I opened is at most B. The probability of me opening, choosing I at V can't be more than the probability that I chose I times the probability that I came to V. These must be probabilities. This is my expected value. Maybe in hindsight, if I'd just given you this LP, you might have believed me a little more easily than going through this exercise. But I wanted to show you the exercise. It's somehow this is how you are arguing about this LP. How did you come up with this LP? It's because you said on every choice, here are some constraints, valid constraints. Then in expectation, this must be true. Okay. By the way, this LP now is nice and small. If there are only, if the values are only between 0 and m, let's say, then there are how many variables are there? There are n boxes. There are m plus 1 variable. So there are so many y's, and the x's are only n of these guys. Okay. Okay. So here is an LP which captures the optimal decision tree. Sorry, it is a relaxation of the optimal decision tree. The optimal decision tree has all kinds of other constraints I don't even know. But all these constraints are true for the optimal. So if I am maximizing, so to actually capture the optimum, I might have other constraints. I don't know. Shouldn't we use equality constraints? We could use equality constraints. I won't need them. We could use equality. In fact, because you're maximizing, both these constraints will turn out to be equality. Good. And the formulation on the right. So, I find it difficult to say that there is an IP that's going on because it's a decision tree. So I don't quite know how to, say that this is the right-hand side is an integer program and the left-hand side is the fractional thing. But in some sense, yes, it's a relaxation. Okay. More questions. Okay, so let me suppose you believe me for the moment that the left-hand side, this LP is at least opt because I'm maximizing. So it's at least, it's capturing opt and maybe more. So now let me just show you the rest of how to get an algorithm out of this LP. How do we get an adaptive strategy? So Bernardo, you're absolutely right. So wait for this slide and then ask me the question again. So all I know right now is, the LP or some, I have some guess for what the probability with which the optimal strategy opens box I, which is xi, and what is some, what is the probability with which optimal strategy chooses box I at value v, yiv, right? These are kind of my guesses. This is what my LP is giving me. I need an algorithm out of this. Come on, guys. So let me give you an algorithm. So here's the algorithm. By the way, there's you'll notice a box at the end, right? That means that the proof is going to end there. So the whole proof is on this slide. So the pain is only bounded. There's very little pain. Okay. So here's the algorithm. The LP says, I'm going to open box I with xi probability. So let me open box I with probability xi over 2. I'll be a little cautious. Okay. Good. Now, if the this should be, so let me call this Vi. Let the variables be called V1 through Vn from now on, because x's there are too many x's floating around. So I've changed my notations. Okay. So if the value of the ith box is equal to little v, choose it with what probability? Yiv divided by xi times piv. And you should really think of this as like a conditional probability. Okay. I mean, it's right now it's just a numerical value. Let's run with this, and you'll see why. Okay. My claim is that this algorithm gets an expected value of the LP divided by 8. By the way, this algorithm is clear, right? I mean, I solve this LP, I look at the XI and YIV values, and I run this algorithm. So I start going over the boxes from left to right. And let's say, so for I equals 1 to n. I look at box 1, I open it with some probability. If I am allowed to open it, there's some probability with which I won't be able to open it, because of, and if it takes on value v, I choose it with this condition probably. Okay, and my claim is the algorithm gets this value. Okay. So one thing to note is that the expected number of boxes I open is b over 2. Why? Because of this constraint. I open box I with probability xi over 2. The xi's sum up to b. So the expected number of boxes I open is b over 2. Okay. How many things do I choose? Okay. My claim is that the expected number of boxes chosen is at most half because of this constraint. And maybe let me skip that for a moment. Suppose you believe these two constraints. Suppose you believe these two claims. Okay. Okay, what happened? Come on, guys. You can. Good. I'll say I'll reach a box I. Remember, I'm going boxes 1, 2, 3, n, right? I'll reach a box I if I have opened fewer than b boxes earlier, and if I have made fewer than one choice earlier. Suppose I've not made a choice and I've not opened b boxes yet, then I can open the next box. But the expected number of boxes I'm going to open is b over 2. So the probability that I've opened b boxes is at most half. The number of choices I've made in expectation is 1/2. So the probability that I've made one choice is at also 1/2. So each of these events that I'm blocked because I've either opened a box, I've chosen a box or I've opened too many boxes, happens with probability 1/2. And in fact, these events you can show are positively correlated. If you sort of have opened a lot of boxes, you're more likely to have. Okay. So the probability that I pick I with value v is, well, I should reach I. Once I reach I should open I. Once I open I should see v. Once I see v, I should choose it. There are 4 quantities. I reach I with probability 1/4. I open it with this probability. I see it with that probability. And I choose it with that probability. And that's it. This is why I chose. And now you'll see why this number was chosen, right? I mean, it's kind of like this conditional probability of you opened it and you saw this value. So this is conditioned on that. This is the probability with which you open, with which you choose it. Okay. And you just multiply these together. It's yiv over 8. So, okay. So let me just make that last thing. So this is the probability with which my algorithm picks I at value v. So the expected value I will get is summation. Summation over v times yiv over 8. This is my expected value, at least, which is LP over 8. By the way, so okay. let me say this in a slightly different way, and then so here's the point I want to make. Somehow, if I'm opening a box with this probability, and I'm seeing the value I for that box with that second probability, maybe I should just use the pointer. If this is the probability of opening the box and this is the probability of seeing the box, then just condition on that. This is like the conditional probability of choosing. Okay, that's all we did out here. Okay. Why did we open boxes with small probability? I just want to make sure that I don't use up my budget too fast, that I get to every box with some probability. Okay. So this is why I scaled it down. And this is a feature that you will see again and again. I want to make sure, I want to be a little cautious. I want to make sure that I have a chance of trying everything. So this is just me being cautious.
Sorry, but so where does it appear in the calculation? Because here you just have like the expectation, right? So
good. So the place where this cautiousness appears is exactly, I'm saying that in expectation, I'm going to open up only B over 2 boxes. So the probability that I have already used up all my boxes is at most a half.
Yeah, okay. So, but you could turn to 1 minus epsilon, or is it?
Good.
Yeah.
So, good. So if I do 1 minus epsilon, then I need to use some kind of concentration. And for the number of boxes opened, it's easy to do. The number of boxes chosen is the hard one to do because it's only 0 or 1. So here's a great extension if you want to sort of test yourself. Suppose I allowed you to choose K boxes. You open B and you choose the top K. Try to get sort of a value which is much closer to 1. It's not like 1/8 or something like this. Try to use concentration for this and you will be able to. And maybe, I can give more details later on. You're absolutely right. Okay, why is the expected number of boxes chosen 1/2? Okay, and let's just do that calculation very quickly. The expected number of boxes chosen is the expected. Okay, so I'll choose a box with probability what yiv. So first I should open that box. That box should take on that value. And I should then open it. And then I should choose it. And this is true over all possible choices of boxes and values. So this is the expected number of boxes chosen. And this is exactly summation yiv divided by 2. And that constraint says it's 1/2. It's just coming from the fact that you're shading everything down by a factor of 2. By the way, this slide looks like a complete mess by now. Yeah. If something's unclear, ask again. Yeah, good. Okay, so maybe let me say two more things about this. Actually, there's sort of many things that I would like to say more about this, but maybe let me just say here's the high level idea. We took our stochastic problem. We wrote this LP. This LP doesn't capture everything about the stochastic problem, but it captures some of the decisions we were making. It's saying what's the probability with which various decisions were made. Okay. So this was this LP on the right-hand side. We kind of rounded it to get an integer solution, but it's not really like an integer solution, right? I mean, it's we got this strategy on the left. And then we kind of interpreted it. We said, oh, this is really a policy. I'm going to open this box with this probability. I'm going to open this box with this probability. I'm going to, if this happens, then I'll choose this. And so I interpreted it as a stochastic policy. And maybe, this flowchart doesn't make that much sense to you, or maybe you'd like a better flowchart, feel free to. This is just an interpretation of what we are doing. But the whole point was you wrote down just marginals. You wrote down just marginal probabilities. And this idea, by the way, is not new. So there's a famous, one of the first game theory Nobel Prizes is to Roger Myerson, who developed the optimal auctions for single items. His algorithm is really, it takes an auction, it writes down an LP, but the LP is much bigger. It's an exponential sized LP. But thankfully, this LP can actually be solved exactly because there's some modularity going on or something. And he shows that LP value is exactly equal to the optimal auction. Okay? His problem was different, our problem is different. But really, this idea of looking at marginals is not a new idea. And it can be extended. Okay. But maybe let me, good. Keep opening. Yeah, absolutely. So Bernardo, that's a very good point. So Bernardo asked, why did we stop in the middle? Why are we doing this decisions on the fly? Why don't we wait until the end? And that's a reasonable thing. Your value will be no less than what the value of this algorithm is. You might be able to get more. I don't know how to get more in the analysis. And this analysis is simple, so I just went with this analysis. But what you could do is you could just open all the boxes that this algorithm opens and then look at the maximum value and just choose that. You're spot on. There are some advantages to this, this algorithm. It's what we call query commit. You look at a random variable and immediately you say, oh, okay, I'm going to choose you. Or you say, sorry, buddy, not going to happen today. In some cases, this is useful. It's like when you're selling items, you don't want to look at everybody's bid. You might, people might come in, they say, I'll give you $50 for this. You say, no, not going to happen. What is best box after all? It's like, getting the most money out of, N buyers who are going to come. Only you're allowed to ask B people for bids. Okay? So it works in this online setting. And some of you had already noticed that some of these problems are related to so-called profit inequalities. If you've never heard of profit inequalities, don't worry about it. But if you have, these are related to profit inequalities, and the connection will come up more next time. Okay. You might say the factor of 8 is not very good. And you're right, it's not very good. But you can improve it. I'm just giving you the simplest proof. You can get a factor of 3. You have to work a little harder, but that's okay. We can work hard. What's a lower bound? So I can show you a lower bound, which is E over E minus 1. But I don't know how to close this gap. Okay. So it might be a sort of an interesting direction. Okay. Can you get a 1 plus epsilon approximation? Now, I already showed you a gap of, like 1%, 2%. So I can't always get a 1 plus epsilon approximation where epsilon is really tiny. But can I be slightly adaptive? Right now, I was being very non-adaptive. I just wrote down, I just went down this list and, I flipped coins. Maybe I should be, a little more adaptive, like Bernardo's idea. Cristobal has a great question. Does non-adaptiveness need randomness? I don't know. Okay. So here is the thing. It doesn't need randomness if what you could do is you could come up with the best non-adaptive strategy. So in some cases, you can actually, explicitly come up with the best non-adaptive strategy. So this is just saying there exists a non-adaptive strategy, which is pretty good. But in many cases, what we do is we get non-adaptive strategies using rounding, and then we do randomized rounding.
So Anupam, can I maybe elaborate a little bit further? I'm not sure if I'm understanding correctly, but when you do adaptive versions of this, you could just go through the tree and optimize the conditional expectations, and
Absolutely.
those extreme conditions would be deterministic. So it seems to me that optimal adaptive strategies can be deterministic.
So optimal adaptive strategies, in fact, should be deterministic because you can de-randomize. Yeah, exactly.
Okay.
There is no reason to randomize. You should choose the best one of these options.
Right. Okay,
Absolutely.
thanks.
So the decision tree is a deterministic object. Absolutely. Okay. And more broadly, just this idea of looking at marginals is like a simple idea. Now, one more thing that maybe I should mention, is can you add more constraints? So these were some constraints that the optimal policy satisfied. And this was the value that we were guessing. This is our estimate of the value. Can you actually get a tighter relaxation by adding more valid constraints? I've tried and I've not been successful, but it doesn't mean anything. I would love to see, and this is one of my favorite problems in this thing, add some more constraints that can actually make this LP tighter. Go down the Roger Myerson route. His constraints don't work, by the way, so whatever those are. Okay, so, as you can see, I had my plans were a little crazy. So I'm going to stop here. There's a lot of stuff in here. Have a look. Feel free to ask me questions. Some of you sent mail yesterday with a couple of questions. I was very happy, and I'm happy to answer more questions as they come up. But the slides are there. Have a look at them, and we can talk some more. But maybe the thing that would be fun is if you're comfortable with what we did in this first part. That would be great, because that will lead very nicely into the next lecture that we'll do. Victor asks, are there similar approaches when the distributions are continuous? Indeed. So there are similar approaches. Now, if they're continuous, then you need some way of optimizing this LP. But basically, if you can somehow write some surrogate for this LP, maybe by discretizing at suitable values. Usually, okay, short answer, if they're in some bounded range and you have some estimate of opt, you can do some discretization. If they have a nice parametric form, you can actually replace these sums by integrals and do some trickiness with that. If they are general continuous distributions, it's a little more difficult to say anything meaningful. Cool. Other than that, there's a whole bunch of stuff. I'm going to ignore all that, and maybe I'll just mention that the next time we'll use some of the same ideas to come up with algorithms for whatever these things are, profits and secretaries. These are just two kinds of online decision making. These are very cool, cute applications, but with applications of their own to algorithmic game theory and all that sort of thing. So I'll talk a little more about that on Friday. I guess tomorrow we have a day off. But cool. So let me stop here and take any questions that you guys have.